I am recording. All right, so we went 71 first. So 71, let me move this up a little bit. 71, I have CHHH connected to an N, triple bonded to a C. Agreed?
Yes.
That is going to C to H to H to H. This one is connected to a C, which is triple bonded to an N.
Does the end of the C literally just switch places? Is that the only thing? The triple bond, does that just switch small?
Well, I'm making sure I do this right.
Wait, pause. Nitrogen, that's only 246.
Well, there'd be a lone pair out there, but we don't really care about the lone pair for bonding, right?
Wait, also, oh yeah.
Okay, sure.
Yes?
Yes.
So the only thing that's changing is this and that.
That's what I was asking. Is that the only?
That's it. This bond is broken, this bond is formed.
They just swap places.
Is that like number 4 on the review sheet?
I don't know.
Yeah.
It might be.
Okay.
So this bond, carbon nitrogen, is 305. So it's going to be 305 kilojoules per mole times 1 minus carbon to carbon is 347 kilojoules per mole times 1. So this is going to be exothermic because you end up with negative 42 kilojoules.
Okay, question.
Yes.
So if you don't see what's changing, could you technically add up the left and right sides?
Sure. Why couldn't you?
I don't know, I just wasn't sure.
That's going to be a lot more work.
Facts.
But yes, you could add up the left and right sides. That would work. What?
Add them up and then subtract them.
Yeah. Well, you would have to do, yeah, that would work. Next one,
Okay.
88?
86C.
86C.
Is it negative 42 kilojoules?
So we have 86C, I have HCN, it's kilojoules, because that's technically times 1 mole, right? The moles canceled out. Right? So I have 1 plus 4 plus 5. So we need a total of 10 valence electrons, yes? So carbon always goes in the middle. So here's my basic, right? Can I add anything to hydrogen?
No.
No. So I could potentially put lone pairs on the carbon. So if I put a lone pair here, right? That'd be 2, 4, 6, 8, right? Is that going to work for nitrogen? So I got a triple bond, right? And add a lone pair. That's the only way you can draw that one. It actually will not work any other way.
Wait, did you demonstrate that? I don't really.
Well, if I try like this, hydrogen, carbon, if I put 2 lone pairs there, right? And I tried to double bond here, I would still have to put, I actually can't even double bond there, right? Because carbon can't have an expanded octet. So in order to fill up nitrogen, I would have to have how many lone pairs? 3, 2, 4, 6, 8, 10, 12, 14. It doesn't work.
Okay, while we're on that, the expanded octet applies for BPS.
Expanded octet does not apply to the boron.
Expanded octet is phosphorus and above.
Phosphorus is
Yes.
as in like anything that has.
If it's the central atom, it can have more than 4 pairs.
Boron, beryllium,
Because, oh, right,
lithium,
because
and
Boron and
They
below,
have a little line thing. It shares the electrons. So it, like,
correct.
stays.
The line counts as 2. Yes.
and then boron is
Was there another one on 86 or 88 you wanted to see?
Yes.
Which one?
88 just had a bunch of ions.
88, I think I need to see B.
All of it?
No, just A1, NF3.
NF3. So 88B, I have NF3, 7, 5 times 3, 21. So I have 26 to show, right? So,
Oh,
N,
it's gonna be
F,
two,
F.
there.
So I know, right? It's going to be 8, 16, 24. It's going to be a lone pair,
2, 4, 6, okay.
right? So that was B. Which other one?
105A.
Anything else on 88?
Negative.
88D, which, oh. What conclusions can you draw concerning the structures of species containing the same number of atoms and the same number of valence electrons?
They're similar. They're similar structure.
Yeah, because they have the same number of atoms, right? Same number of valence electrons. They're all going to be like all with 3 lone pairs. So it should be pretty much the same. What else?
Might as well. 105A.
105A.
They love giving us the.
105A? Let me make sure I'm on the screen. 105A. I have POCl3. Phosphorus is 5. Oxygen is 6. Chlorine is 7 times 3. 21, 27. That's going to be a total of 32, right? As soon as you see that, right? You know it's just going to be phosphorus,
My thing
O,
was, How
Cl,
do we know phosphorus in the center?
Cl.
compared to oxygen?
Well, you want to have phosphorus in the center because it's the only one that can have the expanded octet. So you put that there in case.
Chlorine have to expand back that. There's phosphorus in the middle.
Well, chlorine, there's 3 chlorines. If there's multiple, they're always going to go on the outside.
So if you had oxygen in the center, you'd have.
That's not going to work. If you put oxygen in the center, the formal charges will not work out.
Okay.
What, did you demonstrate that?
Yeah, I think I need to see it.
So if I put O here, Cl, 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 P, right? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6.
Oxygen.
1, 2, 3, 4, 5, 6. Oxygen does have 8. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Formal charge of chlorine. It has 7. It has 7, right?
Yeah.
So I got a 0, 0, 0. Oxygen has 6, right? So this is a negative 1.
Oh. Okay, yeah, that's not good.
And then,
Wait. No, that's supposed to be 0. Their formal charge is
well,
0.
phosphorus has 5, right? 5 minus 4 is
Oh, okay.
positive 1. So this has an overall charge of 0.
Which is what you want, because it's, if they have.
On this one, oxygen has how many? 6. 6 minus 4 is plus 2. This phosphorus has how many? 5, right? It has 5 valence, yes. 5 minus 7 is negative 2. And these chlorines are still going to be 0.
So you have a formal charge of 1
Oh.
plus 1? No, it's 0.
So it's still going to be formal charge of 0.
Okay, wait. So then why
So hold on, let me think about this. What number is this?
105.
105A. Well, it's just because phosphorus is the only one that can have the expanded. You put the one in the middle that can have the expanded octet. But O can't have an expanded octet. I wonder what the book says.
This is.
Because when in the compounds, when you need an expanded octet, you want that one in the middle.
Okay.
So
Like
just
you always go for the one that
just always put it in the middle.
Make it so the expanded octet goes for.
Oh, wait. I know why. Remember for formal charges.
You want the negative on the most electronegative element, right?
What?
You want the negative formal charge on the most electronegative element, right?
Correct.
Phosphorus has a negative.
Phosphorus is not, right? The most electronegative is oxygen, yes. So first of all, that should be negative. Second of all, when you're doing formal charges, if they both add up to 0, it's the structure that has the lowest formal charges.
Oh, that was in the notes.
That's a +1 -1. This is a +2 -2. There we go. I knew that there was something with formal charges there. I just couldn't. Monday. What?
Are we gonna have to like,
You'll know. You'll know on the test which one's the center. You'll know.
Like you'll tell us or?
No, you'll know.
Okay. You'll just know.
You'll know.
That's good.
You all
know, John.
And like FCF2, it has to be easy.
Right. Next question.
Uh,
Aubrey, are you okay with that?
I think
Okay.
it's number, I can't even know where this starts at. Oh, it's probably 105 too. It's like the IF3.
105, I've got, this is letter, that's not 105.
Or whatever it is, I don't even know.
That's.
There's 121 has an ICL3.
Maybe what's one IF3?
IF3.
Memorized?
Oh, that's 127.
Okay, yeah.
127B.
Yeah.
So 127B, IF3. These are all, that's a 7, right? That's going to be 21, that's going to be 28, right?
8, 16, 24, and then 2 sets of lone pairs or a double bond and a lone pair.
Well, I, F, right? 2, 4, 6, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So there's my 24.
Except I is not.
So I need 2 more, I need 4 more electrons, yes?
Yep.
It's going to be 2 lone pairs. It's going to be 2 lone pairs.
I think you do a double bond and then 2 on the end, or 4 on the end.
Okay, well, let's try it. So if I have an I, F, why can I not write today? Oh my gosh. F. Oh my goodness. Hold on. It's Monday.
It really is Monday.
Oh.
That's an F, okay? I can't write the letter F. I'm having like a seizure or something right now.
Oh gosh.
You're saying a double bond here.
Yeah, and then 4.
So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Let's count it. 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24.
We'll lone pair 2 on I as well.
Well, that will give me 26.
So I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 4, 26. That's only 26.
Shoot. Wait.
So what am I going to do?
Because the double bond.
So I'm going to put 2 lone pairs? That doesn't make sense. I'm not going to have 2 lone pairs with a double bond. Right now I'm showing 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. That does not make sense. Why would I have 2 lone pairs and a double bond? That doesn't make sense. Right? So it really does not make sense to add you only add a double bond if you have to. What's the molecular structure of this?
T-shape.
That's T-shape. It's T-shape.
And then the EPS is 5, so it would be.
EPS would be trigonal bipyramidal.
Okay, I was doing this morning. What's the difference between EPS and the molecular structure again? One's like what's
EPS is the total number of sites. So EPS, I've got 1, 2, 3, 4, 5 sites.
So that's looking at it 3D wise. Like, does that make sense? What I mean by that?
EPS is just counting. We don't even really care about the shape for EPS. EPS is literally just counting. I've got 1, 2, 3, 4, 5 sites. So my EPS is trigonal bipyramidal.
6? I don't see 6.
There's 5.
5, okay.
There's 1, 2, 3, 4, 5.
Okay.
The MS, I ignore the lone pairs and I only look at the molecule.
I can remember the T-shaped one.
So that's T-shape.
Oh, that's
Because it's literally a T.
Well, that's how I drew it.
Well, it's like a sideways T. It's like a.
You don't draw.
Oh, it's a.
If you don't draw it like that, then you got to know what that is.
If you see a lambda in that, I can sort of see it.
Next question.
It's only 128 and 129 left, right?
Okay, wait. First.
8, can we do HOCN, please? And 128.
Sure.
Number 2.
So 128A, HO. This is what they gave me, right?
You have double bonds.
So let's add it up. I have 1, 6, 4, and 5. 9 plus 6 is 15 plus 1. I've got a total of 16. So I'm going to have H to O to C. So there's my base, right?
Yes.
I've got 2, 4, 6 showing. And I know the oxygen has to have 8. I know carbon has to have 8. I know nitrogen has to have 8. So let's just see if I can do, I'm just going to, in my head, see if lone pairs would work for everything. So if I put 2, 4, 6, 8, 10, 12, 14, right? 16, 18, 20, that's not going to work. Agreed? So I know I'm gonna have to have some double or triple bonds. I know that nitrogen likes to do what kind of bond? Triple bond.
Something like nitrogen,
Well, nitrogen has 5, right? So nitrogen likes a triple bond. So I put a triple bond there. Nitrogen's happy.
Is that like, sorry, is the triple bond basically because of one side of the pole?
Exactly. You got it. So nitrogen, is nitrogen happy yet?
No.
carbon is
I want to put a lone pair there. Agreed? So now I've got 2, 4, 6, 8, 10,
Oxygen.
12. So oxygen's going to have what?
not.
2 lone pairs.
What is, can you, is it possible to do the, like, the structures for this, like, the molecular structure and the electron?
I could do the molecular structure for every one of these if I wanted to,
Oh,
right?
individually, not the thing as a whole, though.
Yes, you have to break them up.
So like oxygen would be bent.
Yes.
Right?
Yes.
This would be linear, right?
But the overall thing, like.
No.
You can't.
You can't.
Wait, why are both of the lone pairs at the top?
Because they want to have the most repulsion. So that was 128A. Anything else on 128?
Yeah, can we just do the rest of them?
The rest of them. B, COS, 4, 6,
Oh, COS is kind of weird.
6. So this is a total of 16.
I see it.
Carbon always goes in the middle. Carbon, O, sulfur. So that's 4. If I put 2, 4, 6, 8, 10, 12, all right, that would work, but carbon's octet wouldn't be full. Agreed? If I just had lone pairs on each side. So I'm going to try double bond, double bond. 1, 2, 1, 2, 1, 2, 1, 2, 2, 4, 6, 8, 10, 12, 14, 16. Got it. So I kind of think in my head, will just lone pairs work? No. Then it's going to have to be some kind of double or triple bond. That was 128A. I should probably check and make sure I'm getting these right, but I know I am.
Linear?
The shape of this? Yeah, that's linear.
Is it because there's the double bonds of equal?
Is this polar or non-polar, by the way?
Non-polar.
This is polar. Here's why. Because these are not the same atom on each side. Right? So that's polar.
Do the double bond, like that's like how it is. Like would there be like a larger like resistance, like
What about the
to,
other
like
one?
different shapes? If there's like a double bond.
A double bond actually kind of looks like this. It's actually kind of curved.
Okay.
Is the HOC polar? Probably is.
Yeah,
There's no chance that's not polar.
that's definitely polar.
Look at it, let's look at it, there's no chance.
Would you look at that? C, I have X, E, F, F. I need a total of 8 plus, I need a total of 22, right? So if I put 1, 2, 4, 6, 8, 10, 12, lone pairs isn't going to work, right?
Everything,
Xenon is one of the ones that you can bond.
everything you know is wrong, everything you know.
So let's see. What if I did this? 2, 4, 6, 8, 10, 12, 14, 16, 8, 20, 22. So that one actually does work with all lone pairs. Because xenon can have an expanded octet.
Xenon, why is xenon have noble gas bonding? Like, why?
Because it's special.
Yeah, I was about to say, why is it even bond?
I'd have to look up why it's bonding, but it's possible.
What are the other, if you know, what are the other noble gases that can?
It's mostly just xenon.
Xenon.
It's just like that.
Xenon's
Just like that.
No different.
And this is,
Polar or non-polar?
No, not polar.
It's non-polar because remember those are actually evenly distributed around the central thing.
and then what the structures would be
Linear.
linear.
Wait, for an expanded octet, can it be
The
like-
EPS would be tri-bipyrate, the EPS.
Wait,
1,
for
2,
all-
3, 4, 5. Yep, try by
And
pi.
then
So
the
for an expanded octet, how many electrons can it have? Is it just like infinitely many?
6 at the most.
Not applying
You'll never
to-
have, well, I'm sorry, 12
12.
total, but 6 sites.
Okay.
You never go past 6. D, I have CF2, CL2, CF2, CL2. So 4, 14, 14. So I've got a total of 30, right? C,
No,
F.
32.
You're right, I can't add. 32. Why is this hard?
It's not. Oh, wait, I had a question. So,
8 times 4 is what?
32.
So it's just gonna be 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, done.
This is a full module, right?
Yep,
So my question is, when
They're
you're
not
writing,
symmetrical.
correct.
Is it non-polar?
Polar.
does it matter where you put, like, I have like my F's alternating,
I don't care.
does it not matter?
Nope, it's 3D. It's 3D. So that was D, E. I have S, E, F, 6. 6 times 7 is, 6 times 6 is 36. Plus another 6 is 42. So I'm going to have SE, 1. I'm thinking in my head, that's going to be,
No. 7 times 6 is 42, plus 6 is 48.
It's 6 plus 6
Seven.
times.
6 times 6 is 36.
Fluorine has 7 valence. Fluorine has 7 valence, it's 48.
6 times 7 is
42. It's 48 valence.
48. Thank you. Good call. So now I'm thinking in my head, as I'm adding these up, 8, 16,
Oh, I see.
24, 32, 40, 48.
And it's capped, you can't add it more.
Am I going to need any lone pairs?
No.
No,
Add anyone?
I can't.
Okay, but SE, wait, SE would be 2, 4, 6, 8.
And it has 6 bonds, I thought you said you couldn't add
Oh,
more
it's
than
got
6
the
bonds.
expanded.
This has 6. 1, 2, 3, 4, 5, 6. That's
Can you
allowed.
add any more?
No.
Yeah, okay.
It's capped.
So electron pair is
Octahedral.
octahedral or square bipyramidal. MS is the same.
Do you have any more lone pairs than the SC? Than it-
No, you cannot add anything else to the SE.
What would happen?
And SE is an expanded octet.
It would explode.
That's how that works.
Oh, it'll explode?
Yes, I'm not kidding. And F, I have H2CO, so 2, 4, 6. That's going to be a total of 12. Carbon, hydrogen, hydrogen, oxygen. So that's 6. So if I tried lone pairs, 8, 10, 12, 14, that's not going to work, right? So I'm going to double bond my oxygen and try 2 lone pairs. 2, 4, 6, 8, 10, 12. That works. That's polar. Wow, I'm off the screen. You guys should have told
It
me.
looks so cool. You can tell by looking at it.
It's very polar.
Any other questions?
No, but can we go to the review sheet, because there's something I don't understand.
Sure. Which one?
I think it's just doing the ionization energy.
On number 3?
In the example that we did, like, in the notes,
Uh-huh.
we didn't take like 1/2 of 154.
We didn't have to. On this one, so on this one, and you guys understood you were solving for x on this one, right? Yes. So on this one, I'm taking 1/2 of 154 because I have F2, but here I only have 1/2 F2. So I have to divide this by 2. That's why.
That one's really easy.
Yep.
And then I think it was B on number 5.
Oh, lithium oxide?
Yeah, Li2O.
What about it?
That's ionic. Can you still draw like an over this structure?
Why not?
Can you show that one? Oh wait, you have it right there.
So I need a total of 6 plus, I need 8, right? So 2, 4, lithium can't have more than 2, right?
Does the duet rule apply to all group 1?
Well, I mean, I guess not necessarily. But lithium, I guess lithium, it's not going to, right? Because the first shell of lithium is 2, right?
So does the duet rule apply to hydrogen and lithium?
Sure. Because lithium isn't going to have more than 2, right? So 2, 4, 6, 8.
Okay.
You're not going to double bond a lithium.
A double one.
You will not double bond a lithium. And then I drew it like this. Sometimes you'll see it like this, where they just put the lone pairs instead of bonds. But you might see that. Anything else on
Why
this?
does the nitrogen one have like little big dots? Oh, it's
Because it's resonance. The double bond can go on any of them. So then I drew the 4 on this one.
Very, very quick question.
Yes.
6. This was the like extensive hydrocarbon.
Oh, this one made no sense.
The one thing I have is how did you know that the final hydrogen was attached up to the carbon? Like,
This one.
yeah, how did you know that the final hydrogen wasn't in between?
So I have CH2, right?
Yeah.
Double bonded to a C. Why is it not here?
Yes.
Because I can't expand that octet. It already has 4 things connected.
Now, what do you mean by the number of pure p orbitals? Like,
Oh yeah, what is the pure people?
Pure P, just pi bonds.
so there's one.
Pure P and a pi are the same thing. So C1, right, has 1 pi bond.
Yep. C2.
C2 has 1 pi bond. C3 has 2 pi bonds.
You said the triple bond.
Because a triple bond, the second and third. A pure P is the same as a pi.
Okay.
And the pi bond is the one with more than one.
Correct. Pi bond is anything after the first bond. Single bond, 1 sigma. Pi bond is anything after that.
And really quickly, can you kind of explain number 3? Like according to the molecular orbital theory?
That is, well, molecular orbital theory is not really on the test, but paramagnetic, right, means that it's unpaired. I think I did this in the notes.
It was in last chapter.
I think that might have been last chapter. Para means unpaired, so that if they're unpaired, that means it will be affected by a magnet, because that means that there's room for them to be attracted. Whereas if they were paired, they don't want to, they're already paired off.
Was
So
that
I have
one,
2
like,
open orbitals.
One where it got like attacked by like the whatchamacallit?
It might be. So if it's like this, it's not going to be attracted to a magnet. If there's open spots, it's going to be attracted to a magnet.
Question for isomers. Can you say molecule molar structure?
Sure.
Okay.
Isomer is the same thing as resonance, essentially. Yep.
Okay, and then
This chart took.
can I see the work for 4? Because I don't know what this means.
On the front,
Yeah.
so on the front,
So,
I have, let's see,
so
I'm breaking 2 of the triple bonds, right?
yeah, but did you say to just go on what's changing? Well, technically,
that is
all's
changing.
right?
I broke everything.
Yeah.
So I broke 2 C triple bonds. I broke 2 H to C's. 4, because there's 2, there's 2 times 2 is 4. So I broke 4 of those. I formed, over here, C double bond O, 2 times 4, which is going to be 8. And I form my water, OH, I have 2 of those. 2 times 2 is 4. So make sure when you have coefficients, you're multiplying that through for your number of bonds.
Okay. And then number 2. Why does
Oh, and also here, did you divide it by 2? Because I asked for 1 mole of acetylene. In the problem, this is for 2, right? So you got to divide by 2. So watch out for something like that. That's something easy way to miss a point.
Okay, and then for number 2.
Yes.
Why? Is it because Mg has the most protons? Like,
These are all what?
so they're all any. But,
These are all isoelectronic. Right? Agreed?
Yep.
Magnesium has the most protons.
Okay, that's why.
So that's kind of a throwback to last chapter.
Do you want us to draw the chart for number 3?
No,
Okay.
don't draw the chart.
I'm a visual. I have to draw it out.
If you want to, you can. But you don't need to.
I'll bring that.
That's just going to waste time.
What even is that chart? I don't really get it.
It was in the notes.
Up and then
Oh,
back
right,
down.
that one.
Yeah.
Okay.
I feel like, well, technically you could just add them all up and then you gotta figure out which one you got.
You're just adding them up and seeing if you need to change something. Yeah.
Okay, I think that's it.
Do you want to do a couple cahoots? Yeah, let's do it. Couple cahoots. Get out your Chromebook.
There's not gonna be like any of the math ones on this, right?